So we call it as one bound, but it's a double bound, it's a triple bound, they're different. Okay, so how do we determine the total number of valence electron pairs? We count the total number of bounds, single bound or double bound or triple bound, doesn't matter, and then plus the number of lone pair electrons. And then once we have that number, once we have that information determined there, the steps to determine the shape and to make the prediction about the geometry, draw the Lewis structure, okay, and focus on the central atom there, and then count the total number of valence electron pairs. Once you get all this information, once you have the Lewis structure there, then there's a table in your textbook. And if you do enough practice, you may memorize all of them, you may remember all of them, but I don't need you to memorize this. I'll give you this table there. Okay, so this particular table indicates the number of electron pairs. When you have 2, 3, 4, 5, and 6. Well, when you get 6 electron pairs there, and that's a total of 12 electrons. That pretty much covers all the exceptions that we can have, but when you have as many as 12 valence electrons on the central atom there. And this particular table gives you, based on the number of valence electron groups that we have here, you can determine how many of them are bounding groups, how many of them are lone pairs. And when you have bounding pairs versus lone pairs there, the electron group geometry, well, electron group geometry does not depending on the bounding pairs or lone pairs. It only depends on the total number. Okay, so if you have 2 valence electron pairs, it's going to be linear electron group geometry. When you have 3, you could have 3 bounding pair, no lone pair. You could also have 2 bounding pair, 1 lone pair. Okay, so that's a situation there. Now in this particular case, if you have 3 bounding pair and no lone pair, then the molecular geometry will be trigonoplanar. But if you have 2 bounding group and 1 lone pair, okay, then the molecular geometry is going to be bent. So this is the table that we need you to use to make predictions there. And each situation we give you the bound angle, and not the exact bound angle there. It's when you have trigonopyramidal, when you have bent in tetrahedral structure with the tetrahedral electron pair geometry there, only say it's going to be less than 109.5. Methane as a quintessential representation of tetrahedral structure there, 109.5. That's a bound angle, very important bound angle there. But when you have lone pair of electrons involved, it's going to be less than 109.5. Water, 104, ammonia, 107, and so on and so forth. And these are the Lewis structures with those different types of molecules there, and these are the models, the model that you will be playing with, some of the models you will be playing with in the lab tomorrow. Okay, so this is the table that I will give you. In the final exam there, I'm going to give you this table there. If we ask you questions about the molecular geometry, all you need to do is to be able to draw a Lewis structure, focus on the central atom, determine the total number of valence electron pairs on the central atom, and then you look at this table and you determine the geometry. So let's try water, H2O. Now, I gave you the same list for Lewis structure. It's the same list that we need you to draw a Lewis structure for. Now, water, H2O. Okay, ammonia, the second one. We have those in the Lewis structure on the board already. Okay, so in this case, if we ask you to determine the geometry of these molecules, their electron group and the molecular, the Lewis structure is drawn, focusing on the central atom, oxygen in this case, nitrogen in this case. Okay, on the central atom there we have 1, 2, 3, 4, total of 4 valence electron pairs. Well, go back to that table there. Total of 4 valence electron pairs. Okay, we have 4, one situation here. 4, one situation here. 4, one situation here. So this is the situation that we have here. Among these 4 electron pairs, 2 of them are bounding, 2 of them are lone pair. So this line is what we're looking at. For the electron pair geometry, though, it's tetrahedral. It only depends on the total number of valence electron pairs there. When you have 4 valence electron pairs, it's tetrahedral. Molecular geometry is bent because you have 2 bounding pair and you have 2 lone pair. Okay, you have a bent geometry. Water is an example here. So you know the Lewis structure drawn this way doesn't actually represent the actual situation of the molecule. And when you draw the Lewis structure of water, to draw them at an angle there, approximately 105 degrees. Okay. So ammonia, well, this is a Lewis structure for ammonia. 1, 2, 3, 4, four valence electron pairs. So going back to this table, 4 electron pairs, electron group geometry is going to be tetrahedral. It only depends on the total number there. Now in this case we have 1, 2, 3. 3 bounding pair, 1 lone pair. So in this case we have 3 bounding pair with 1 lone pair. Electron pair geometry is still tetrahedral. Molecular geometry is trigonopyramidal. Okay, so this is how you use this table. Now, when you look at these molecules, the first 2 examples, there is only one central atom in there. So when you talk about the geometry of a molecule with only one central atom, you're talking about the geometry of the entire molecule. What happens if you have molecules with more than one central atom? Well, when you talk about the geometry, molecular geometry, and you hear the term molecular geometry, you're thinking, well, that's the geometry about the entire molecule. We're talking about the geometry around each central atom. So when you have more than molecules with more than one central atom there, you determine the shape or the geometry around each central atom. So it's not about the entire molecule. So example, if you have acetic acid, the acid in vinegar, okay, we ask you to determine the geometry of these particular molecule there. And obviously in this case you have 2 carbon and oxygens in there, and both carbon and oxygens can be central atoms in there. So in this case we have C, write out the Lewis structure. Oops. Okay, this will be the Lewis structure, and this is what I expect you to be able to do when you finish this course there before you get into organic chemistry. So CH3, COOH, this will be the Lewis structure for acetic acid. Now, you won't get to how fast I draw the Lewis structure until you do multiple repeated practice there. Okay? So if you look at the Lewis structure there, well, you still follow the general steps of drawing the Lewis structure. Okay? So in this case, you count the total number of atoms, and you count determine the central atom there, and then distribute the electron pairs there. So when we're talking about the geometry, we're talking about the geometry around this particular carbon, this particular carbon. Now this oxygen is also a terminal atom there around this particular oxygen. Okay, this is a terminal. This is a terminal, 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 terminal. You don't. When you talk about the geometry there, you are talking about the geometry surround the central atom there. So for this particular atom there, okay, we have carbon in the center, 1, 2, 3, 4. All 4 of them are bounding pairs. So the geometry for this carbon is tetrahedral. We're talking about the molecular geometry. Electron group is also tetrahedral because you have 1, 2, 3, 4. And going back to that table there, and that previous slide there where you have that table there. Okay, this carbon, 1, 2, how many? 4 or 3. Well, for the purpose of determining the geometry, the double bound, we only count them once, because these 4 electrons occupies the same similar region in space. Therefore, they exhibit one repelling force to other electrons there. Okay, so we don't count